In the beginning there is silence, pure, unbroken silence, the kind that predates language and matter, a silence so deep that even the notion of a beginning is itself a kind of intrusion. Out of this primordial hush, a singularity stirs, a seed infinitesimal and infinite all at once, and from it erupts the event we call the Big Bang. 14 billion years have spilled forth since that first furious instant, and in their wake, galaxies have unfurled like spiral arms reaching across a dark and frigid canvas. Stars have kindled and died, and planets have spun themselves from stardust. Somewhere in all this splendor floats a question as ancient as the cosmos itself. How does it end? Is there a final silence waiting to reclaim everything? Or does the universe spiral towards some more dazzling, terrifying denouement? It is a question that has haunted the minds of thinkers and dreamers for centuries, echoing in the long corridors of time. The first astronomers, their eyes trained to the heavens through polished brass tubes, wondered if the stars would someday fade. Philosophers debated the eternity or finitude of all things, while theologians spoke of creation and apocalypse. In the 20th century, as Edwin Hubble discovered the expansion of the universe, a revelation that shattered the steady, eternal cosmos of Newton and Laplace, science itself was forced to grapple with the possibility of an ending. The universe, it seemed, was in motion, and what is set in motion must either find rest or run to ruin. A century later, the question has grown sharper, more urgent and infinitely more complex. Astronomers wield tools that peer billions of years into the past, giant telescopes perched on remote mountaintops, space observatories floating above the distorting veil of Earth's atmosphere, detectors chilled to near absolute zero, in search of the faintest whispers of cosmic radiation. Physicists conjure equations that twist and loop through dimensions beyond human intuition, mapping the subtle interplay of matter, energy, and the unyielding fabric of spacetime. Theorists debate in the language of entropy, quantum fields, and dark energy, striving not only to describe the universe as it is, but to divine its ultimate fate. And so the modern conversation turns around four great themes: the inexorable decay of entropy, the collapse of a big crunch, the catastrophic unraveling of a big rip, and the unfathomable power of black holes to consume and transform. Each theory is a window onto a different future, a different death for everything that has ever existed. Each is anchored in the latest discoveries, shaped by the gravitational pull of new data and bold conjecture. What follows is a journey through these endgames, a deep dive into the mysteries and revelations of cosmic destiny. The concept of entropy, the arrow of time, is the first specter to rise. Entropy is the measure of disorder, the tally of all the ways a system can be arranged. In the 19th century, Ludwig Boltzmann and Rudolf Clausius gave it mathematical form, encoding in their equations the tragic fact that energy, once spent, cannot be wholly reclaimed. The universe, they showed, is a vast engine running down, its order bleeding away into chaos. Every star that burns, every cell that divides, every thought that flickers in the human mind is an act of borrowing from a finite reservoir of usable energy. The second law of thermodynamics demands that this borrowing must end, and with it, so too must the story of creation. In this vision, the universe ends not with a bang, but a whimper, the so-called heat death. Over unimaginable eons, galaxies will drift apart, their stars burning out one by one. Brown dwarfs and black dwarfs will outnumber all else, their faint glow a whisper of bygone brilliance. Even the black holes, those titanic engines of destruction, will eventually evaporate in a slow drizzle of Hawking radiation, their mass leaking away into the void. The cosmos will become thin, cold, and dark, a place where no work can be done, no thought can arise, no complexity can survive. This is the universe as a graveyard, entropy as the gravekeeper. But entropy does not have the final word, for there are other possibilities, equally strange, equally final. Consider the Big Crunch, a theory that once reigned supreme before dark energy entered the lexicon of cosmology. In this scenario, gravity is king. The expansion of the universe, set in motion by the Big Bang, is eventually slowed and reversed by the mutual attraction of all matter. The galaxies halt their flight and begin to fall inward, accelerating toward a final collapse. The temperature of the cosmos rises once more, reversing the arrow of entropy as everything is squeezed into an ever-shrinking volume. In the final moments, the density and heat become infinite, a mirror of the beginning. Perhaps, some have speculated, a new universe is born from this cataclysm, the cycle beginning again, forever. Yet the Big Crunch's rule was short-lived. In 1998, observations of distant Type Ia supernovae by two teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, revealed a shocking truth. The universe was not just expanding, but accelerating. Some unseen force, dubbed dark energy, was pushing the galaxies apart faster and faster, in direct defiance of gravity's reign. This discovery, honored with the Nobel Prize in Physics in 2011, upended the cosmic narrative and set the stage for a new cast of endings. Dark energy is now estimated to make up roughly 68% of the total energy content of the universe, dwarfing the contributions of dark matter and ordinary matter alike. Its nature remains elusive, perhaps a cosmological constant, as Einstein once postulated in his equations of general relativity, or perhaps something stranger, a dynamic field whose properties evolve over time. What is certain is its effect. The fabric of space-time itself is stretching, and the rate of stretching increases with time. The fate of the universe, it seems, is governed not by the pull of gravity, but by the push of this inscrutable energy. Here emerges the most unsettling of all fates, the Big Rip. If dark energy grows ever stronger, if its density increases rather than remaining constant, then the acceleration of the universe's expansion will also increase, not merely separating galaxies but tearing apart everything. Galaxy clusters, galaxies, solar systems, planets, molecules, atoms themselves. In this scenario, derived from models of so-called phantom energy, with an equation of state parameter W less than 1, the end is sudden and violent. Long before the final instant, the night sky becomes empty, the Milky Way alone in the darkness. Then the solar system dissolves, the Earth shreds, and ultimately even the molecules and nuclei that once composed us are ripped asunder. The timeline for this apocalyptic vision depends on the properties of dark energy, but some estimates suggest a mere 22 billion years from now, an eye blink on cosmic timescales. Between these extremes lies a quieter but no less profound fate, the one implied by a universe dominated by a cosmological constant, an unchanging dark energy. Here the expansion continues forever, but at a steady pace, not a runaway. Galaxies drift beyond one another's horizons until each is an island universe, isolated by the swelling void. Stars die, black holes evaporate, the universe grows dark, cold, and empty, a heat death, but one shaped by the accelerating expansion, rather than by gravity alone. This is the so-called lambda CDM scenario, the standard model of cosmology, which best matches the data collected by the Planck satellite, the Sloan Digital Sky Survey, and countless telescopes around the world. But the universe is nothing if not surprising, and the role of black holes promises further twists. These monsters of space-time, whose existence was first hinted at by Carl Schwarzschild in 1916 and confirmed by the detection of X-ray binaries in the 1960s, are now understood to be ubiquitous, lurking at the centers of galaxies and in the hearts of stellar remnants. They are the engines of quasars, the forges of gravitational waves, the sculptors of galactic evolution. But black holes are not eternal. In 1974, Stephen Hawking showed that quantum effects at the event horizon allow them to emit radiation, a faint, ghostly glow now known as Hawking radiation. Over trillions upon trillions of years, even the most massive black holes will shrink and vanish, leaving behind only the faintest imprint on the vacuum. Recent discoveries have deepened the mystery. The detection of gravitational waves by LIGO and Virgo has revealed a population of black holes with masses previously thought unlikely, mergers of 30, 50, even 80 solar masses. The Event Horizon Telescope has imaged the shadow of a supermassive black hole in the galaxy M87, confirming the predictions of general relativity with exquisite precision. Meanwhile, theorists like Roger Penrose, Kip Thorne, and Juan Maldacena have explored the paradoxes of information loss, suggesting that the ultimate fate of the universe may depend not just on the decay of matter, but on the fate of information itself, whether it is lost forever in the abyss or somehow encoded on the shimmering surface of the event horizon, preserved in the quantum foam. Consider, too, the possibility of vacuum decay, a nightmare born from the equations of quantum field theory. If the universe's vacuum is not truly stable, but only metastable, then a fluctuation could trigger a phase transition, a bubble of true vacuum expanding at the speed of light, rewriting the laws of physics as it goes. Everything, stars, planets, atoms, would be annihilated, replaced by a new and alien order. This is a fate indifferent to time, always lurking, always possible, a shadow on the edge of existence. And yet, for all the chilling grandeur of these theories, the universe is not merely a machine grinding toward oblivion. It is a tapestry woven from paradox and possibility, and every new discovery reveals not closure, but deeper mystery. The cosmic microwave background, detected by Penzias and Wilson in 1965, mapped in exquisite detail by Kobe, WMAP, and Planck, speaks of a hot, dense beginning, but also of a universe whose precise fate depends on the delicate balance of energy, matter, and geometry, the baryon acoustic oscillations, the distribution of galaxies, the dimming of distant supernovae. All are clues in a puzzle that has not yet yielded its final answer. The fate of the universe is thus a question of physics, but also of philosophy, a meditation on the meaning of time, the nature of existence, the possibility of renewal. Each theory offers not only a prediction, but a story, a vision of what it means for something to end, and what, if anything, might come after. As we journey deeper into these endgames, let us linger in the realm of entropy, the silent thief. Imagine a universe in which time itself is defined by the increase of disorder, the slow drift from improbable arrangements to the most likely, the descent from order to chaos. Entropy is the specter that haunts every process, every act of creation. Even at the smallest scales in the dance of molecules and the flicker of quantum fields, the second law is absolute. In the words of Arthur Eddington, the law that entropy always increases holds, I think, the supreme position among the laws of nature. Yet entropy's victory is not immediate. The universe is vast, and its reservoirs of order are deep. Stars burn for billions of years, their nuclear fusion converting hydrogen into helium, radiating light and warmth into the darkness. Out of the ashes of dead stars, new worlds are born, life emerges, complexity flourishes. For a time, entropy is held at bay by the creative fury of gravity, the relentless drive of chemical evolution, the improbable emergence of consciousness. But the end is inescapable. As the stars die, as the last red dwarfs flicker out, as the black holes evaporate, the universe cools and dims. Eventually, only the faint glow of Hawking radiation remains, a universe populated by ghosts of energy, structure dissolved, memory erased. The timescales are staggering. The last stars will die in about 100 trillion years. Brown dwarfs and rogue planets will persist for longer, but without new sources of energy, their fate is sealed. Black holes, the final repositories of matter and energy, will take far longer, up to 10 or 100 years for the most massive to evaporate. After that, only a thin, cold soup of photons, neutrinos, and other light particles remains. This is the heat death, a universe at maximum entropy, where no gradients remain to power change, thought, or life. For many physicists, this is the likeliest fate, supported by the data and the iron law of thermodynamics. But it is not the only possible ending. The Big Crunch, once favored in an era before the discovery of dark energy, offers a more dramatic closure. If the density of matter were just high enough to halt the expansion, gravity would gradually slow the flight of galaxies, then reverse it. The universe would contract, heating as it shrank, until all matter and energy was compressed into a singularity, a mirror image of the Big Bang. Some have speculated that this collapse could be followed by a bounce, a new Big Bang birthing a new universe. In this cyclic cosmology, the universe is eternal, oscillating between expansion and contraction, creation and destruction. Alexander Friedman, Georges Lemaitre, and later Richard Tolman all explored such models, seeking a way to reconcile the observed expansion with an eternal cosmos. More recently, the ekpyrotic and cyclic models inspired by string theory, developed by Paul Steinhardt and Neil Turok, have offered new mechanisms for such bounces, involving the collision of higher dimensional brains. Yet the data do not favor such an ending. Measurements of the cosmic microwave background, the abundance of light elements, and the distribution of galaxies all point to a universe that will expand forever, its density too low to reverse the flow. The discovery of dark energy, an acceleration rather than a deceleration, seems to seal the fate against a big crunch. Still, the theory remains a haunting possibility, a reminder that the universe's fate is not written in stone but etched in the shifting sands of observation. The Big Rip, by contrast, is a newcomer, a product of the strange properties of dark energy. If dark energy is not a cosmological constant, but a form of phantom energy, with an equation of state more negative than 1, the expansion of the universe accelerates without bound. The scale factor, describing the distance between any 2 points in space, diverges to infinity in finite time. Everything is torn apart. The mechanics are chilling. First, distant galaxies drift beyond the cosmic horizon, their light lost forever. Then the gravity-binding galaxy clusters fails. The clusters dissolve. Next, galaxies themselves are ripped apart, stars flung into the void. Solar systems disintegrate, planets separated from their stars. In the final instance, the very bonds that hold atoms together are broken. The universe ends not in a slow fading, but in a cataclysm of disintegration. Observationally, the Big Rip is only possible if dark energy's properties are extreme, if its density increases over time rather than remaining constant. Current data from supernovae, baryon acoustic oscillations, and the cosmic microwave background suggest that the equation of state parameter W is very close to 1, consistent with a cosmological constant, but the uncertainties remain, and future observations, perhaps from the Euclid mission, the Vera C. Rubin Observatory, or next-generation gravitational wave detectors, may yet reveal surprises. The role of black holes in all these scenarios is both destructive and redemptive. Black holes are the ultimate engines of entropy. When matter falls into a black hole, its information is thought to be lost, scrambled beyond recovery, increasing the universe's total entropy. Yet black holes also represent an escape from the ordinary laws of physics, a window onto quantum gravity, the unification of general relativity and quantum mechanics. Stephen Hawking's discovery that black holes are not truly black, but emit radiation due to quantum effects near the event horizon, was a revelation. Hawking radiation is incredibly faint. It would take longer than the current age of the universe for a solar mass black hole to evaporate completely, but over vast timescales, it ensures that even the most massive black holes will not last forever. Their evaporation is a kind of slow, ghostly sigh, a return of mass and energy to the vacuum. The fate of information in black holes remains one of the deepest problems in theoretical physics. The so-called information paradox pits the deterministic evolution of quantum mechanics against the apparent loss of information when matter falls into a black hole. Recent work by Maldacena, Susskind, and others on the holographic principle and firewalls suggests that information may be preserved, encoded on the surface of the event horizon, accessible in subtle correlations of the Hawking radiation. The final answer may reveal new principles of physics, perhaps even pointing the way toward a theory of quantum gravity. What then do the latest discoveries suggest? The data favor a universe that will expand forever, its fate governed by dark energy. The standard model of cosmology, lambda CDM, matches the observations with remarkable precision. The cosmic microwave background, mapped in exquisite detail by the Planck satellite, reveals a flat universe with a dark energy component consistent with a cosmological constant. But questions remain. The nature of dark energy is unknown. Is it truly constant, or does it vary over time and space? If it varies, could it become negative, reversing the acceleration and triggering a collapse? Or could it become more negative, accelerating the expansion toward a big rip? The answer lies in the faintest signals, subtle shifts in the brightness of distant supernovae, the clustering of galaxies, the polarization of the cosmic microwave background. Meanwhile, black holes challenge our understanding of the ultimate limits of physics. The detection of gravitational waves by LIGO and Virgo has opened a new window on the universe, revealing the mergers of black holes and neutron stars, the ripples of space-time itself. The Event Horizon Telescope's image of M87N, and the mass and spin measurements of black holes in binary systems constrain the properties of gravity and the fabric of space-time. Quantum gravity remains elusive. String theory, loop quantum gravity, and other approaches strive to unify the laws of the very large and the very small. The information paradox, the nature of space-time singularities, the fate of information in black holes, all are portals to new physics, new understanding. Vacuum decay, the possibility that the universe is perched on a metastable false vacuum, remains a specter. Calculations based on the measured masses of the Higgs boson and top quark suggest that our universe may not be absolutely stable, but only metastable. A quantum fluctuation, perhaps triggered by a high-energy event, could nucleate a bubble of true vacuum, expanding at the speed of light, annihilating everything in its path. This is a fate that could occur at any time, without warning, a reminder of the universe's fragility. Yet for all these possibilities, the universe is resilient. Its fate is written in the laws of physics, but those laws are themselves the product of a deeper order, an order we are only beginning to glimpse. Each new observation, each new theory, is a step toward understanding not only the end, but the meaning of the journey. The story of the universe's fate is ultimately a story about time. Time as measured by the ticking of atomic clocks, the flicker of pulsars, the red shift of galaxies. Time is experienced by living beings, by civilizations, by stars and galaxies. Time as a dimension, woven into the fabric of space-time by Einstein's equations, curved by mass and energy, stretched by the expansion of the cosmos. The arrow of time is set by entropy, by the irreversible flow from order to disorder. Yet time is also a mystery, a veil behind which the deepest truths of the universe are hidden. In the equations of physics, time is often reversible. Run the clock backward, and the laws remain unchanged. But in the universe we inhabit, time moves inexorably forward, carrying us from birth to death, from creation to destruction, from beginning to end. The universe's end, then, is a kind of mirror, a reflection of its beginning, a culmination of its story. Whether it ends in heat death, big crunch, big rip, or vacuum decay, it is an ending written in the language of physics, but also in the poetry of existence. As we contemplate these endings, we are drawn into a meditation on our own place in the cosmos. We are creatures of dust and light, born in the hearts of stars, shaped by the forces of gravity and entropy, animated by the flow of energy from order to disorder. Our lives are brief, our civilizations shorter still, but we are part of a story that began in fire and may end in silence. The discoveries of recent decades have brought us closer to an answer, but the answer remains elusive. The universe may end in darkness, its last embers dying in the void. It may end in fire, collapsing to a singularity or exploding in a final cataclysmic rip. It may end in a phase transition, a rewriting of the laws of physics themselves. Or it may persist, forever expanding, forever cooling, forever changing. In the end, the universe teaches us humility. We are not the authors of its story, but its readers, its witnesses, its fleeting participants. The beauty and terror of the cosmos lie not in its ending, but in its unfolding. The dance of galaxies, the birth and death of stars, the emergence of life and consciousness, the quest to understand. The universe will end, as all things end, but in its ending is a kind of grace, a testament to the power of order and chaos, creation and destruction, time and eternity. We gaze into the darkness, seeking answers, and find instead the wonder of the question. In the far future, when the last star has died and the last black hole has evaporated, when the universe is a thin haze of particles drifting through an endless night, perhaps there will remain a trace, a memory encoded in the structure of space-time, a whisper of the order that once was. Or perhaps not. Perhaps the end is truly final, the silence absolute. But until that day, the universe endures, and with it, the possibility of discovery, of meaning, of wonder. The journey is not yet finished. The story is not yet told, and in the darkness we continue to seek the light.